Okay, Assalamualaikum and good afternoon. So we continue. Okay, we continue our lecture on the Couette flow, but now we go for the third condition, where this is the third condition where the flow is now between stationary parallel plates. So in this condition, we need to take care about the pressure. Might be, maybe. So mean we cannot make a fast decision to neglect the existence of pressure, because the meaning of parallel plates here might be, might be you are now conducting a duct in a square shape. So means, so if the fluid is now fill all this duct here, so it will create something like flow in pipes. But the difference is the cross-sectional is not circular, the cross-sectional is in rectangular shape. So means that if the fluid is now full in this duct, so it means they will create pressure. So as you know, the Bernoulli equation, so when the fluid flow, they will create pressure depend on the elevation and so on. That's why in this situation, maybe we need to calculate the pressure. So and the second one is, now you have it will flow naturally like this one. Okay, it will flow from the upward to the downward here, and we assume that the fluid is now fill all the area inside that parallel plates. So means that if we want to calculate this one, we need to think about the x-axis and also the y-axis, because we have the gravity here. So okay, and then the gravity is, a part of gravity is actually influence the motion of this direction. Okay, because it is inclined at certain angle. So you know, when certain angle, so when you have weight, so you need to distribute it into x-axis and y-axis. So in this direction, so some portion of gravity is actually influenced in the moving of this x direction. So you need to understand like that. So and then, so next, I hope you could understand how to take the boundary condition. So for example, we have the height here is b. So we could say that the velocity at this location, so when y is equal to 0, the velocity is 0. And at y equal to b, because the height here is b, okay, the velocity is also 0. So it is because we assume that at this condition, so the velocity, the molecule will stick on the surface, and because the surface here is fixed, not moving, so means that the velocity is remain equal to 0, then the velocity distribution will show like this. Okay, so this is the example, the assumption for this one. So we start from the basic equation that I show you before we enter the condition number 1. Okay, please refer that equation. And then from that equation, we have the terms of pressure, we have the term of rho gz. Okay, we maintain that one because it's not easily for us to say that pressure is 0 and dz is 0 and so on and so forth. So we keep maintain that that term, and we do the integral twice because as you know, we have d square u over dy square. So we do the integral twice, so we get this one. So now we have the constant parameter C1 and constant parameter C2. So we, by using the boundary condition, we could get that C1 is here. So and then we put into the this equation, and then we give another boundary condition. So we get it is equals C2 is equal to 0. So another thing, this is the rule of thumb. Because we know that the velocity distribution is something like this, okay, so means that because it must start at 0 here. Okay, that's why if you do your calculation and suddenly you found that the value of C2 here is represented with certain integer, so that might be 99.99% is wrong. Okay. Okay, so previously in chapter 1, we do calculation with one condition of slip condition. Means we assume that molecule is not stick on the surface, so the molecule will move at certain velocity. We have that condition and we have that calculation. So if that condition, yes, you may have the value of C2, but in normal liquid in this world, you assume that there's no slip condition is actually occur. So because our graph will start at 0 here, if you could see the trend of the graph, so means it is impossible for you to have an integer here, because it will give you something like at velocity at certain location, so the velocity is exists before it's actually moved. Okay, so that's why we say that the C here must be 0. Okay, you could add the constant is equal to 0 if you know the trend of this graph. Okay, so this is the rule of the thumb, because I have experienced students do the calculation and suddenly they get the value of C2 here. Okay, so and then we get the final equation for the velocity as this one. Okay, so and then so here we just replace the dz over ds into dh over ds, because this is just to simplify the suit with the diagram. So and then we are calculating the maximum velocity here. So we know that from the diagram here, the maximum velocity is actually occur at the middle. So this is the something that you should know. So in this situation, because there are less shear stress in the center line here. Okay, so previously if you have a situation, you have an incline here and then you have water here. So if it is a free surface like this, so the velocity distribution might be like this one. Okay. So but now both is contact with a solid surface, so the velocity distribution will shown like this. So the center line here will have the maximum velocity. So that's why to calculate the maximum velocity here, we substitute with the value of y equal b over 2, and then we could calculate the maximum velocity is like this one. Okay, and then here the value of the negative dh over ds here is actually just to show that the it is showing its flow downwards. Okay. So and then I simplify this one. So I think you understand this equation. So this equation is actually calculating the flow rate here. And then again, we just do from the equation of Q equal AV. So we try to calculate the average velocity. So I also explained about the average velocity previously. So and then this is the notes. So according to this book, they say that less than 1,000 it is laminar, and if it greater than 1,000, so it may be turbulent. So it's a little bit different from what we know about flow in pipe. So because in flow in pipe here, so we could say that if the Reynolds number is less than 2,000, so it will become laminar. And if Reynolds number is greater than 4,000, So it will become fully turbulent. So why the Reynolds number here is different? Because in this situation, they assume that our conduit is in rectangular shape. Okay, because this term, this condition is referred to the circular shape. Okay, so this that's the difference. So the determination of Reynolds number here must be done according to the experimental works, because you know, by calculation need to be verified, need to validate. So normally people will validate with the experimental. So this is the simple example. I think you could read and understand this one. So we have a specific gravity of 0.8. The viscosity is this one, and its flow downward between two vertical smooth surface spaced at 10 millimeter apart here. So if the discharge per meter of width is 0.01 meter square per second, because we assume that discharge per meter of width mean we divide the value of discharge with the width, or we just assume that the width is equal to 1 meter, and we need to calculate the pressure gradient here. So the pressure gradient here is actually can be calculated by this one. Okay, so for example, we have the Reynolds number is 400, and then we could calculate the kinematic viscosity like this one, and then according to the equation we have the dHds is equal negative 0.306, and then we substitute the value of dHds by this equal. Okay, and then we just we could solve this one by assuming that ds dz is equal -1. Okay, so and then we have all of these. So we have dpds is equal 5,447 Newton per meter squared. So this is the simplification one, 5.45 kilopascal per meter of length of plate. Okay, now we try to do the same things to develop an equation for the parallel plate like this, but now we are trying to solve this one by using the Navier-Stokes equation. So I think you could have an idea about this, because previously I showed you. So again, we have this one. Let's say we have this condition. So and then we make assumption. So the first step in using Navier-Stokes equation is you try to simplify your equation, because Navier-Stokes equation is the very complicated equation, and it consists of all parameters. It consists of x, y, and z. It consists of gravity. It has pressure term, and so on and so forth. So let's say, and then because it is fully developed, and then the idea of du dx and dv dx it will equal to 0. So and then because the flow is steady, means the velocity is not changes anymore. So we have the du dt is equal to 0, and dv dt is also equal to 0. And then the component of gravity vector in x direction is y sine theta, and the y direction is negative g cos theta. So and then here might be they use the idea of, okay, because what we have x and y here, we have x and we have y here, because normally upward here is the positive of y, but the gravity will pull downward like this, so they will give you a negative sign. That's all. That's the coordinate system only. But in some textbook, they will just remain the g. They will assume that gravity will have positive value in terms of downward like this. Okay. So you have this value. So let's say we assume that according to the axis here, the gravity is minus. So and then we have a continuity equation, because we only have two axes, mean x and y. So this is our continuity equation. Because we focusing on the rectangular conduit like this, so we are using the Cartesian coordinate, mean x and y. Okay, after this, we will focus on flow in pipe like this one. Then we'll use the polar coordinate, because here we need to take care about the radius r and so on and so forth. Okay, but for now, we are focusing in Cartesian coordinate. So that is the continuity equation. So and then because we assume that du dx is equal to 0, so we only take care about the v dv over dy. So it is equal to 0 according to the rule of continuity equation. So here, please bear in mind that continuity equation must be equal to 0. If your continuity equation is not equal to 0, means that your calculation or your first assumption is not valid. Okay, that's why if you do simulation, the first thing that you need to do is to make sure that your continuity equation is equal to 0. Okay, so and then because our plane now, our system is inclined at certain degree, so means we need to evaluate them by using the y direction and also with x direction. So we go with the x direction first. So so because the v is 0, so the v here means that, so we have a flow here. So let's say this is the u and we have the v here. So we assume that all the molecule here will flow straight line, means molecule will have the u component but not v. So that's why we say that because of v is 0 everywhere, so there is no acceleration in the fluid. So you know that the acceleration means that the velocity is 0. So for sure it doesn't have acceleration. So we could reduce everything in y-axis Navier-Stokes equation here into this one. So and then because we have only dp over dy, and then when we integrate this one, we could have, we bring the dy to the right hand side here. So we have rho g cos theta minus y. Okay, so because we have minus here, and then we integrate y with y here, so you have a minus y, and then you will plus the px here. They mean the constant of pressure at y, at x axis. So and then if you bring these terms for this one, okay, so the condition is when y equal to 0 at x is the pressure distribution along the lower wall. This equation shows that the pressure decrease with elevation in the duct as expected. In fact, y cos theta is equal to z. So this equation can be written as the equation for the hydrostatic pressure variation like this one. So I think you could understand here. So why we know that pressure is equal to rho gh. So we have y cos theta here is actually the equal to h. So we change that value into h or z. So we have this is not rho, this is p. Okay, I'm sorry. So this is p, the pressure. Okay, so the pressure is plus rho gh. Then you get the pressure at a value of x. And then you could rewrite something like this. So this is just for the equation. Okay, that's for the y. But the most important is actually the Navier-Stokes equation for the x. Because in reality, velocity will flow on x-axis. So means that there are a lot of calculation or a lot of element in Navier-Stokes equation need to be fulfilled. So here, I think you could do this because it is value of steady flow. It is also a fully developed flow. And then the left-hand side of this equation will reduce to 0. So another thing here is, okay, so this is now is equal to 0. So and then you will have delta p over x minus delta minus g here. So you bring here to this side, and then you bring here this g here to the left hand side. So and then it is equal to this one. Okay, so because u is a function of y only, so because the idea of du dx is equal to 0, so I explained this previously. So there are no increment of u along the x-axis, and dp is a function of the x. So this equation can be simplified of this one, and then we substitute the value of sine theta with delta z over dx. So dz over dx is also explained previously. And then we could rearrange this one to get this term